What if I told you there's an invisible glue holding literally everything together? From the device you're watching this on to the air you're breathing right now, it's all built by a fundamental set of rules. And today, we're going to pull back the curtain and see what they are.
Have you ever really stopped and thought about it? What keeps a single grain of salt from just, poof, falling apart? Or what makes a copper wire a solid wire instead of just a pile of dust? It's a huge question, and it takes us right to the very heart of what matter actually is.
And the answer? Well, it's both incredibly simple and powerful enough to build entire galaxies. It's chemical bonds. You can think of them as the tiny, invisible architects that construct our entire world, one atom at a time.
So here's our game plan. We'll start with ionic bonds, the chemistry of giving and taking. Then we'll look at covalent bonds and the power of sharing. After that, we'll dive into the wild world of metallic bonds, and finally, we'll line all three of them up to see how they compare.
Okay, first up, ionic bonds. The easiest way to think about this one is as a simple transaction. You've got one atom that has something to give and another one that really, really wants to take it. And that simple exchange, it creates an incredibly powerful connection.
So, at its core, an ionic bond is all about a transfer. A metal atom literally gives away an electron, and a non-metal atom swoops in and grabs it. This little exchange turns them into charged particles called ions, and, well, opposites attract. Their opposite charges lock them together like super strong magnets.
So how does this actually happen? It's a neat little three-step dance. First, the metal atom loses an electron, which makes it a positive ion. We call that a cation. Step 2, the non-metal atom grabs that electron, becoming a negative ion or an anion. And finally, step 3, opposites attract. The positive and negative ions are pulled together, and boom, you've got a bond.
And this is exactly how we get something as common as table salt. Sodium, which is a metal, is more than happy to get rid of its one lonely outer electron. Meanwhile, chlorine, a nonmetal, is desperate for just one more electron to feel complete. So sodium gives, chlorine takes. They become charged ions, Na plus and Co minus, and that powerful magnetic attraction is what forms the salt crystals on your fries.
Okay, time for a little pop quiz. We know that ionic compounds are made of charged particles, right? So, why can't solid salt conduct electricity? But the moment you dissolve it in water, it becomes a great conductor. What's the deal with that? The secret ingredient here is movement. It's all about movement. See, in a solid salt crystal, those ions are locked tight in a rigid grid, a lattice. They can't go anywhere. But when you dissolve that salt in water or melt it, the ions break free. Now they're free to roam around, and because they're charged, they can carry an electric current. It's that simple. No movement, no electricity.
Now let's switch gears. If ionic bonding is all about giving and taking, covalent bonding is all about teamwork and sharing. This is what happens when you get two atoms that both want more electrons, but neither of them is strong enough to just rip one away from the other.
I absolutely love this analogy. Instead of one friend just taking the other's sandwich, they decide to put their halves together to make one whole sandwich that they can both share. That is exactly what two non-metal atoms do with their electrons. They pool them together so that both atoms get to feel like they have a complete set.
And this right here is the biggest difference you need to remember. Ionic bonding is a transfer. An electron literally moves from a metal to a nonmetal. Covalent bonding is sharing. The electrons hang out between two nonmetals. Two totally different strategies to get to the exact same goal, a nice, stable, full outer shell of electron.
And this whole sharing thing, well, it builds some of the most important molecules for life itself. Take water, H2O. That's one oxygen atom sharing electrons with two hydrogen atoms. Or methane, CH4, the main part of natural gas. That's one carbon sharing with four hydrogens. This molecular teamwork is literally the foundation of our world.
So, let's put that to the test. Take a look at these pairs. Which one do you think is most likely to team up and share electrons? Just remember the rule. Sharing happens between two nonmetals.
If you said B, oxygen and hydrogen, you nailed it. Why? Because they're both nonmetals, so they're going to share. Sodium and chlorine, that's our classic metal and nonmetal pair, so that's ionic. Same thing with magnesium and oxygen. It really just comes back to that one simple rule.
Okay, on to our final bond type. And this one, well, it's in a category all by itself.
Metallic bonding is what happens between metal atoms, and its totally unique structure is the reason metals are so darn useful.
The key phrase here, the one you've got to remember, is this idea of a sea of delocalized electrons. It's kind of beautiful, really. Unlike our other bonds, the electrons here don't belong to any one single atom anymore. They've all been donated to this collective pool that just flows freely around a grid of positive metal ions.
So here's how that sea forms. Every metal atom in the structure gives up its outer electrons. Those atoms now become positive ions, and they arrange themselves in a nice orderly grid. But the electrons they lost, they form that mobile sea that just washes over and around all the positive ions, acting like a flexible electric glue holding the whole thing together.
And this sea of electrons explains perfectly why metals do what they do. Why are they amazing conductors of electricity? Because that sea of electrons is totally free to move and carry a current. Why can you bend a paperclip or draw copper into a wire? Because the layers of ions can slide past each other without shattering, all held together by that flexible electron sea. It's genius.
All right, ready for a level-up question. Both magnesium and sodium are metals, so they both have metallic bonds. But it takes way more heat to melt magnesium. So why would its metallic bond be so much stronger?
The answer is all about the charge. A magnesium atom gives up 2 electrons, so it forms an Mg2+ ion. Sodium only gives up 1, so it's just a 1+ ion. That double positive charge on magnesium creates a much stronger magnetic pull on that negative sea of electrons. More attraction means a stronger bond, and a stronger bond takes a lot more energy, in this case heat, to break.
All right, we've covered the transfer, the sharing, and the sea of electrons. Now let's bring it all home and put these 3 amazing bond types side by side.
And here it is, the whole story in one place. You've got ionic bonds that transfer electrons between metals and nonmetals, making things like salt. You have covalent bonds that share electrons between nonmetals to build molecules like water. And finally, you get metallic bonds that create that delocalized sea of electrons between metal atoms, giving us useful stuff like copper. 3 different playbooks for holding the universe together.
So next time you drink a glass of water, or sprinkle salt on your food, or just lean against a metal railing, I want you to remember the incredible, invisible architecture that's at work. These bonds are happening all around you, all the time. So the real question isn't what they are, but what are you going to look at differently now that you know how it's all held together?